Problem number 10 is a difficult problem, but we will walk through it step by step. And we did problem number 9 in class together, so hopefully this is just the exact same steps. So first we've got a non-conducting sphere, and in this sphere, the charge is not uniformly distributed. So we have this equation for how the charge is distributed with respect to the radius. And the first part is for us to find the net charge distributed on the sphere. So we're trying to solve for Q. And the best way to do this is, let me do A up in the corner. We know that rho is equal to charge over volume. And since the charge or a small set of charge is over a small part of the volume, we can also set rho equal to dq over dv. Now, that means dq is equal to rho dv, but we also know that the volume changes with respect to r. So I'm going to do this over here on the side, dv over dr. So the change in volume with respect to r is equal to ddr of the volume of a cylinder, 4/3 pi r cubed. And we take the derivative, which is multiply the 3 in front, that cancels out with the 3 in the denominator, and we get 4 pi r squared. So that essentially is the surface area of a cylinder. Let's go ahead and do our integration here. We've got rho 4 pi r squared, and we also, I forgot to add this to it. If this is equal to dv over dr, this guy right here, if I multiply the dr over it, then dv is equal to 4 pi r squared. That looks weird. R squared times dr. So this is what we substitute in for dv. So then I plug that in. I also know that my rho is a equation that also has r in it. So I'm going to do dq is equal to rho naught 1 minus 4r over 3 big R times 4 pi r squared dr. So I want to bring all the r's together. I want to get rid of all the constants. So my rho naught and my 4 pi are going to get pulled out to the front. And then I'm going to distribute the r squared into each part of my expression here. And I get dq is equal to 4 pi rho naught times r squared minus 4r cubed over 3 dr. And now I can take the integral. I'm going to integrate from 0 to q. I'm going to integrate from 0 to r. Actually, 0 to big R. We'll go with the whole. We want the full net charge, so we're going to go across the entire radius of the sphere, and then I'm going to integrate. So I've got here q is equal to 4 pi rho naught, and I've got r cubed over 3 minus 4r to the 4th over 12, because I'm multiplying my power 4 and I'm dividing it to the bottom, which is 4 times 3. And then from there, I'm going from big R to 0. So I'm going to do it with this expression right here. And then I end up with 4 pi rho naught is equal to, I'm missing something. This R needs to be part of my equation. So I've got r cubed, sorry, big R cubed over 3 minus 4 big R to the 4th over 12R. And then I notice that this reduces that to 3, this reduces that to 3, and I end up with r cubed over 3 minus r cubed over 3. That equals 0. So, believe it or not, the charge is equal to 0 coulombs when we get the total charge distribution on the sphere. Now, all that means is that I have some positive charges within the sphere and some negative charges within the sphere, and they all balance out. Okay, for part B, I want to keep my work from part A. It says derive an expression for the electric field as a function of distance for the region when R is greater than R. So for B1, R is greater than R. I'm going to use this row right here. In this scenario, basically, I've got my Gauss's law. EA is equal to Q enclosed over epsilon naught. Since we're given rho, we know that EA is equal to, and that comes from here, is equal to rho times volume over epsilon naught. But we also know that rho is equal to 0. So that means that if rho is equal to 0, then this is going to be equal to 0, and so the electric field is also going to be equal to 0. So for B, E is equal to 0 newtons per coulomb when when little r is greater than big R. And then for 2, we're going to go through this expression again. EA is equal to, I'm going to take this expression right here and substitute it for rho v naught. So it's going to be 4 pi rho naught. Instead of going from 0 to big R, I'm just going from 0 to little r because little r is less than the radius of my sphere. And then I've got r squared minus 4r cubed over 3r. And then I'm going to integrate that with respect to r. So what I end up with is EA is equal to 4 pi rho naught, and I'm going to integrate, so that becomes r cubed over 3 minus r to the 4th over 4 over 4, that cancels out, so this is 3r. And then I have E times the surface area of a sphere, which is 4 pi r squared, is equal to, again, the right side. And what I'm going to do here is I'm going to pull out my common variables. I've got r cubed and 3, so I end up with 1 minus r, little r over big R. So I can reduce 4 pi's cancel out, r squared cancels out with 2 of the r cubes, and my electric field here is equal to rho naught r over 3 times 1 minus r over big R. And I think in your equation sheet, they might have distributed the 3 in the denominator, but they turn out to be the same equation. Okay, for the graphing portion, let me actually write this out here because we're going to want to use it for graphing. I'm actually going to, I lost an epsilon naught somewhere. This epsilon naught needs to be distributed throughout. It's just a constant, but I lost it, so I need to put it back in. Rho naught times 3 epsilon naught. And I'm going to redistribute the r. That's r minus r squared over big R. Because then I know that E is equal to 0. And that's when it's greater than, let me use a highlighter here. That's when it's greater than R. So I know it's going to look like that. But when we've got my expression here, E is proportional to r minus r squared, I've got a negative quadratic. So I'm not going to graph it yet because it's actually helpful to figure out where we've got our maximum value. So I'm going to do D and E first, and then I'm going to graph it. So let's go down here. In order to find a maximum, we've worked with this many times, so hopefully this is automatic for you. So for part D, I'm going to take my electric field equation and I'm going to take the derivative and set it equal to 0. So dE with respect to r, because r is our radius that changes, is going to be d dr. I'm going to take this expression of E because I like that the r is distributed. So rho naught over 3 epsilon naught times r minus r squared over r. And then I can, this is just a constant, so I can just leave that out. And I get the derivative of r is 1 minus 2r over big R. I set that equal to 0. This ends up canceling out, and 2r over r is equal to 1, and therefore r is equal to r over 2. Hopefully the math for that is pretty easy. So then I can go back to my graph. They're going to be where my maximum value is at. I'm going to just call a arbitrary maximum value there. And I know that it is an r squared here. So it's going to be an upside down parabola. So it'll look like something like this. And in order for us to figure out, let me just label this r over 2. In order for us to figure out what that maximum value is, we're going to do part E. And E is just the electric field at r over 2. So I'm going to take, again, my electric field equation. That's this equation right here. Rho naught over 3 epsilon naught times r over 2 minus r over 2 quantity squared over r is equal to rho naught over 3 epsilon naught times r over 2, let me just kind of separate this, minus r squared over 4 over r. And then notice how this reduces. And then I end up with rho naught over 3 epsilon naught. Let me get common denominators. I've got 2r over 4 minus r over 4, which gives me rho naught over 3 epsilon naught. R over 4. And if I simplify this, rho naught r over 12 epsilon naught is my maximum electric field. And so you can label that in your graph here. Rho naught r over 12 epsilon naught is where it reaches its maximum. And that would be at r over 2 radius. So that would be our final answer.